Welcome back, everyone. Today, I thought I'd make a video that's a little bit different, and instead of go step by step through a tutorial, I actually talk about the architecture of some of the AI voice agents that we're building. So jumping right in, if you're building voice agents today, you're probably starting with the standard setup, right? So that's the transcriber model to transcribe whatever it is that you're saying into text. Then we have an LLM of some sort. Usually we use OpenAI, and then a text-to-speech model so that our agent could actually speak. And we'll have these components in some sort of loop. And that approach, which is often called a wrapper, is great for prototyping. It gets you from zero to hello world really quickly. And while wrappers are great for demos or hackathons or just small projects, they tend to struggle in production. They are probabilistic, meaning they rely on the model guessing the flow of the conversation. And when you rely on guessing, you tend to lose control over reliability and safety. So in this video, we're going to look at the system design required to build actual robust voice architecture. We're going to take that probabilistic engine and introduce something called deterministic state management to building reliable, production-ready systems. So let's get into the design. Here is a roadmap for the design that we're going to be going over today. This isn't just about writing different prompts. We actually need to understand the data flow. First, we're going to look at the anatomy of the pipeline. So that's identifying different components like the ears, the brain, or the mouth of our agent, and find the missing piece that most wrappers leave out. Second, we're going to define the conflict. So this is the core engineering problem, trying to run deterministic business logic on a probabilistic engine. Third is going to be the solution. We're going to introduce finite state machines as the architectural fix. Fourthly, we'll look at a real build. We'll trace the logic of a dentist scheduler, for example, to see how this works in practice. And then lastly, we'll do a deep dive into latency. This is usually like the boss fight of voice AI, which includes handling interrupts and keeping the bot fast enough to feel human. So let's start with the basic anatomy. If you go on GitHub or YouTube right now and look up AI voice agent, you're going to see this linear pipeline everywhere. So first, you have the ear. This is your speech to text component. It takes raw audio bytes and then turns them to a string, which is the same thing as text. Next, you have the brain. It takes that string, predicts the next tokens, and generates a response. Finally, you have the mouth, and this is the text to speech, which plays the audio to the user so we can actually hear what the LLM generated. The problem with 99% of tutorials, and a lot that I've done, is that they connect the ear to the brain. They take whatever the user says and then just pipe it straight into the LLM. But that makes the brain an unguided missile. If the user asks your Python bot to write a Python script or talk about politics, the brain is going to do it, and you don't have much control here. In a production architecture, you need this fourth component, which is the orchestrator. Also, the missing link. The orchestrator would sit between the input and the intelligence. It controls the flow, so it decides if the brain should answer, if a tool should be called, and what context it actually needs. Without this box, you are not necessarily building a complete product, but more so a chat interface where you can speak to your voice agent. So why do we need that orchestrator, and why can't we just let the brain handle everything? It comes down to this fundamental conflict in computer science. On the left, you have the LLM. This system is probabilistic. It works by predicting the next token on a probability curve. Kind of like when you're on your phone texting and you have those recommended words that you can use. An LLM is just a very, very advanced version of that. So it keeps guessing the next token based on probability. This makes it creative, flexible, and capable of understanding human nuance. But fundamentally, it is guessing. It is non-deterministic. For instance, if you ask it the same question twice, you might get two different answers. On the right, we have our business logic. This is deterministic. This is your database, your payment processor, your calendar API. These systems demand 100% accuracy. If the user wants to book an appointment at 2 p.m., the system cannot guess if 2 p.m. is available. It is binary, right? True or false. Here's the problem with wrappers. They try to build a rigid, reliable business system on top of a probabilistic guessing engine. If you let the probabilistic engine drive the deterministic car, chances are the car is going to crash. You cannot build a reliable business on top of guesses without a guardrail. So we need a mental model to understand exactly how this crash happens. And for that, I use the intern analogy. So I want you to imagine your LLM as an intern. On one hand, they're a genius. They have read the entire internet. They know Python, history, medicine, law, everything. That represents the infinite knowledge of the model. And this is why we use LLMs. But the intern has a massive flaw. They have a 30-second memory. Technically, we call this the context window. They can handle any immediate task you give them. But if the conversation drags on, or if you give them too many complex instructions at once, their short-term memory fills up. And what happens when an intern forgets what to do? They don't stop working, they start making things up, or they start hallucinating. If you rely on this agent to manage the entire state of a complex phone call just by remembering it, they're likely going to fail. So let's look at how that failure happens mechanically. So the intern forgets, but what does that look like in the actual system architecture? It looks like context drift. This diagram represents the memory stack of your voice agent. At the top, this is your system prompt. This is the main set of rules for your agent to follow. Usually it's something like, you are a helpful assistant, greet the user and offer assistance, do not use profanity, and something like collect the user's name. Below that, you have the conversation history. Now look at the bottom. This red box is the new input from the user. Every time the user speaks, we have to shove that new data into the context window. But the window has a fixed capacity. It's like a fixed bucket. As you keep pushing new red boxes into the bottom of the stack, the old data at the top has to go somewhere so it can get pushed out. Eventually, the conversation gets so long that it physically pushes out your system prompt out of the window. And if this happens, the agent could forget who it is, it could forget the rules, and it could forget its main purpose as a dentist scheduler. This is why long conversations with simple wrappers always devolve into hallucinations. We need a way to manage this memory so the important rules never get pushed out. And that brings us to our solution, which is the finite state machines. And it's probably a word that you have not heard since college or your theory class, but it is pretty important here and it can be broken down very simply. So we know the intern has a bad memory, and we know if we let the conversation pile up, the system crashes. So how do we fix this? We don't try to make the intern smarter, and we don't try to make the context window even bigger. Instead, we change the architecture entirely and we move to finite state machines. This looks simple, but it solves the context drift problem mathematically. Instead of one giant prompt that says you are a dentist scheduler and also handle insurance and also handle payments, we break the brain into tiny isolated rooms or states. And the system can only be in one state at a time. For instance, if you are in the greeting state, the only thing the LLM knows how to do is say hello and ask for a name. It physically cannot try to process a credit card because that logic does not exist inside of this greeting state. And to leave this room, you have to pass something called a transition rule. This is a deterministic gate. We are not guessing if we should move on. We are checking if name detected is equal to true, or in other words, if the AI has detected that the user has provided their name. And this is the most important part. When we successfully transition from greeting to qualifying, we dump the previous context. We don't need to remember the specific hello tokens anymore. We just pass the extracted variable or the name to the next state and reset the stat. This means your context window never fills up. You can talk to this bot for 5 hours and it would be just as fast and accurate as if it was the first 5 seconds. So that is how you solve the memory leak. But let's move on. We are going to architect the dentist scheduler that I mentioned earlier. This specific diagram represents the happy path, or when everything goes right. We start the call in the greeting state. The LLM has a very specific system prompt here. Its only goal is to say hello and ask, who is this? And crucially, the LLM is restricted. It cannot discuss insurance. It cannot check calendar availability. Those tools are not loaded. So if the user asks about them, the LLM is forced to say, I need your name first. Now the user responds, I'm John. In a wrapper, you would just shove that text into the next prompt. But here we use a transition trigger. We run a classification check. Did we detect a name entity? If the answer is true, we would then move to the qualifying state. Now, and only now, does the bot have permission to ask, do you have insurance? So we have effectively routed the user to the next stage of the funnel. But what happens when the user doesn't follow this path? That is where most bots break. Obviously, users don't follow the happy path all the time. They are messy, they get distracted. So what happens if in the middle of the greeting, the user asks, is it raining? In a standard wrapper, the AI would try to answer that. It would hallucinate a weather report, waste tokens, and completely lose the context of the appointment. But in a finite state machine architecture, we handle this within a self loop. The logic checker looks for a name. It sees that the name underscore detected variable is still equal to false because the user did not provide any name. So it will classify this input as noise. Instead of moving forward or crashing, it triggers a specific action. Ignore and reset. It ignores the weather question entirely, stays in the greeting state, and reprompts the user, sorry, I didn't catch your name. Who is this? It forces the user back onto the rails. This is how you make an agent stubborn enough to actually get the job done. Now, let's look at handling complexity. Eventually, you'll hit a fork in the road. Does the user have insurance or are they paying cash? This is just a standard decision diamond. If they say yes, we transition up to the insurance flow. This state has its own unique rules. It'll ask for the member's name. It asks for member IDs, provider names, and other things like that. But if they say no, we go down to the cash flow. Now, this seems obvious. You might be saying to yourself, isn't this just a simple if-else statement? And you're right, but here is the architectural superpower of separating them into two different states, which is called sandboxing. If we look at the cash flow we just entered, the user is here to pay. In a standard wrapper, you would just prompt the model, you are in the cash flow, don't ask for insurance. But prompt engineering can be weak. If the user tricks it, the model still might ask for an ID. In a state machine, we don't just ask the model to behave, we sandbox the tools. When the system enters the cash flow state, we only load the specific function calls the model will need for that state. So that would be something like ask underscore payment and charge underscore card. Crucially, if we had a tool like ask medical history, that would not exist in the state and the model would not know about it because it's not in the function definition list sent to the LLM. This means your bot physically cannot hallucinate, for example, a HIPAA violation, where we are invading the privacy of someone's health information. It can't ask for a member ID because it doesn't have the hands to do it. This is the difference between a bot that might be safe versus a bot that is guaranteed to be safe by design. And finally, now we're going to talk about the pinnacle of voice AI, which is latency. So we've handled logic and we've handled safety. Now we have to handle latency and interrupts. If I interrupt a human, they stop talking immediately. If I interrupt another standard AI wrapper, it keeps talking for 3 seconds because it's already generated this audio file. It can feel robotic or rude. Here is the architecture to fix that. We run a VAD, or a voice activity detection, in parallel with the speaker. If you've done a lot of projects with LiveKit and pipecat, you've probably seen this. It is what is used in those scenarios and pretty commonly when building voice AI agents. But what this does is, even while the bot is still generating audio, the ear is wide open. And you can see that right here. The moment the user speaks, the VAD fires an immediate hardware-level halt signal, which goes straight to the text-to-speech engine. And this is the engineering detail that most people miss. When you send the kill signal, the text-to-speech engine still has 2 to 3 seconds of audio left in the buffer, or the queue. And if you don't delete that, the bot will finish its sentence after you told it to stop. So the orchestrator must physically dump the audio buffer. It deletes the queued byte. This ensures the bot shuts up instantly. If you don't build this loop, you don't really have a conversation. It's more so like 2 people lecturing each other. So to finish this off, AI voice wrappers are fun. They're great for prototyping, and I've made a ton of them on this channel. But if you want to build a system that can handle 10,000 calls without hallucinating, crashing, or annoying the user, you need to stop writing scripts and start building architecture, state machines, sandboxing, interrupt handling. That is the difference between a toy and a product. If you like this deep dive, check out the code in the description, and thanks for watching.